So now that we talked about parallel programming concepts, let's turn our attention to how Java supports those concepts in practice. And this will focus on, quote, modern Java. So there's a number of different frameworks that Java supports that enable parallel processing. The classic way is through something called the fork join pool. And that's essentially an object-oriented framework. And we'll spend a bit of time in the class talking about that. Although that topic is going to be covered in more detail in my concurrent object-oriented programming course next semester, because it's really more about objects than functions. What we will focus a lot on are the next topics. One is going to be streams and parallel streams, where parallel streams is an optimization to sequential streams. And that's essentially a synchronous functional framework. And by synchronous, I mean that you can do blocking operations in threads, and when you make an invocation with various so-called behaviors, the intent is that they can block, and there's a pool of threads to make sure that they continue to make forward progress. A more interesting framework is called completable futures, and the completable futures framework is a so-called reactive asynchronous functional framework. And this framework is just absolutely the coolest thing. We're going to spend quite a bit of time talking about this later in the semester. You'll get a chance to play around with this and other stuff like parallel streams in the programming assignments. But basically what you can do is you can create asynchronous tasks that perform computations, and while the computations are running in the background, they give you back something called a future or a completable future. And then you can have other tasks that depend upon the successful completion of asynchronous tasks. And when those asynchronous tasks complete, then the dependent task can start to run. And so you can do some really cool forking and chaining and joining together of asynchronous tasks in a very, very powerful way. Those of you who've played around with JavaScript might be familiar with this concept, because JavaScript supports something called promises that's kind of along the same lines, although completable futures are way cooler. And then the other paradigm we're going to talk about in this class, which is something I've added new since last time, is reactive streams. And this is an asynchronous programming paradigm that's concerned with processing streams of data and propagating changes from publishers to subscribers. And here we're going to be talking about frameworks like RxJava and Project Reactor, which build upon the standard Java reactive streams API in order to provide very, very sophisticated support for reactive programming. And really cool. This will be the first time I've really taught this material in a course at Vanderbilt in earnest, and I think you're going to like it a lot. It's really kind of the cutting edge of parallel functional programming these days. Let's talk briefly about the Java parallelism frameworks and how they embody those models we just talked about. So the first framework we're going to talk about is the fork join framework. This came along in Java 7, which I think was released about a decade ago or so. And it's an object-oriented framework, which means that you have to use inheritance and dynamic binding in order to customize the abstract classes that it defines and the interfaces it defines and so on. And what the fork join framework provides, the capabilities it gives you, is it gives you a high-performance, fine-grained task execution model for data parallelism. And this is essentially the fork join model, which is kind of that split, apply, combine model we talked about earlier when we talked about the concepts of parallel processing. So you have some kind of source of data, and you fork the source of data up into atomically small chunks. And those atomically small chunks are then run sequentially per chunk, but parallel for all the chunks. And they're mapped to underlying processor cores. And then as each chunk finishes being processed, then they're joined back together again to give you a final combined or merged result. And you can take a look at the link at the bottom of the slide here to learn more about this model. It's a really cool model. And this is kind of the workhorse under the hood for all the other parallelism frameworks we're going to talk about, or many of the other parallelism frameworks we're going to talk about. The secret sauce to understanding the fork join model is this concept of divide and conquer. I'm sure you're familiar with the concept of divide and conquer if you've taken data structures or algorithms courses. For example, if you've taken the 350 course here at Vanderbilt, or I guess let's say 3250 course, they keep changing the numbers, 3250 course, or you've taken the data structures course, the 2201 course. They talk there about divide and conquer algorithms, things like quicksort or merge sort and so on. And the basic idea is that you solve a big problem by either solving it if you have a big problem, you split the problem up into smaller chunks, typically by dividing each chunk in half, and then you go ahead and fork new subtasks to handle each chunk that you've subdivided, and then you compose all the results back together. And you keep splitting things until you reach a point where the problem is so small that you can solve it directly in a sequential way. So that's the basic idea. So it's splitting things up into smaller chunks. Again, quick sort, merge sort, classic examples of how to do this. The way it works under the hood in Java's fork join framework is by using something called work stealing. And I'm not going to belabor what work stealing here is at the moment, but basically the idea is when you've got a pool of threads, each thread has something called a double-ended queue or a deck of work that it's supposed to be processing. And if one thread in the pool ends up with an empty deck, so it's not playing with a full deck, what it does is rather than block, waiting for something to show up for it to do, it'll go to somebody else's deck and steal work that thread in the pool doesn't have time to work on yet. And the idea is just to keep all the threads crunching away and working away in parallel and keep them as busy as possible, thereby maximizing overall utilization of the processors. So that's the concept of work stealing. We'll talk a lot more about work stealing later, so I'm not going to hold you responsible for work stealing until we talk about it in more detail. Given the Java 7 object-oriented fork join model that we just talked about, the framework that was embodied for the past decade, in 2014, Java 8 released 2 new parallel functional programming frameworks. And both of these frameworks end up using or being capable of using the underlying fork join framework, but they provide functional programming facades on top of the object-oriented fork join framework to make them a lot easier to program. One of them is the parallel streams model, where you basically have these pipelines of processing nodes or processing units or processing modules, or what they're called aggregate operations in the nomenclature of streams. And what they can do is they can partition the overall source of data, which is typically something like some kind of Java collection, into multiple substreams that can run independently and then be combined to provide a single reduced result. So this is basically just providing a functional programming wrapper on top of the underlying object-oriented fork join framework. And what makes this so powerful and really, really easy to program is the fact that the parallel streams framework can map the computations onto the underlying threads in the fork join pool without having to expose any of those details to the application developer. The application developer just thinks they're writing a pipeline of composed functional tasks or behaviors using lambda expressions and method references. And under the hood, as an optimization, the parallel streams framework maps that to the underlying fork join pool. And that's what actually does the computations on the various processor cores using all the work stealing and other cool stuff that the fork join pool framework can do. It leverages a specific type of fork join pool called the common fork join pool. And there, as the name implies, there's one of them, and they're shared by all the different parallel streams within a given application process. Parallel streams provides a fine-grained parallelism functional programming model. So unlike the fork join framework, which is a fine-grained data parallelism object-oriented programming model, the parallel streams give us fine-grained data parallelism using functional programming. So it's easier to program, no need to do inheritance, no need to do other things that are more accidentally complex, which is what happens with the fork join framework. Instead, you just say declaratively what you want to have happen. The next framework, and we're going to talk about sequential and parallel streams after we get done with this introduction. We're going to start going into the stream stuff, probably starting next week. The next framework is the completable futures framework. This is a really powerful framework, but it's not as easy to program as streams and parallel streams. So it better darn well give you something in return. And what it gives you in return is performance and scalability. What completable futures allow is the ability to support dependent actions that are triggered automatically upon the completion of operations that are running asynchronously in the background in a pool of threads. And again, this is one of those paradigms where I could explain it to you in a correct way, and it would make absolutely no sense if you didn't understand the concept of futures and asynchronous processing. So I'm not going to belabor the overview here. I'm just going to tell you this is super duper cool. And the asynchronous operations that run basically allow the computations to occur without blocking the caller. So that's really what asynchrony means in a nutshell. It means that the thread that invokes the operation is not the thread that runs it, and the thread that invokes it, which we call the caller, can go off and do something else while the callee executes in the background in a thread from a pool of threads. And that's what's typically called asynchronous computation. The asynchronous operations, of course, can run in parallel in different types of thread pools. You can use the common fork join pool. You can use the various other kinds of pools that you might be familiar with if you know a lot about Java, like fixed size thread pools or cached thread pools and so on. You can even make your own thread pools if you want. And so this flexibility gives completable futures more generality than parallel streams, which is limited to the common fork join pool for some good reasons. It's also possible to combine completable futures and streams so that you can have asynchronous computations that are coordinated by a sequential stream. Now, again, at this point, since you don't know probably a whole lot about either of those paradigms, that benefit or that virtue will not be very enlightening or motivating. But when we get done with other parts of the course, you'll see how cool they are. Then with Java 9, they added some new capabilities. This was the probably the 2017 timeframe, 18 timeframe. I always forget when Java 9 came out. But basically, they added support for so-called reactive streams using the Flow API, which is really just a set of interfaces that doesn't do much other than give you a common way of describing how you want to connect publishers with subscribers. And reactive streams implements a so-called stream-oriented pub-sub or publisher-subscriber framework that embodied two patterns that I'm hopeful you're familiar with from taking the 3251 course at Vanderbilt. And the two patterns are iterator, which is a pull model where subscribers pull items from a publisher. So the subscribers will they'll say, I want X number of items, please, and then the publisher will publish that many items. And then there's also a combination with another very famous pattern from the design patterns book called the observer pattern, which applies a push model that reacts when a publisher source pushes an item to a subscriber sink. So iterator and observer are the two key patterns that are implemented in the Java 9 reactive streams model. Now, the way it actually works under the hood, or not under the hood, the way it actually works above the hood, because this is what you program, is in terms of popular reactive stream implementations, things like RxJava and things like Project Reactor. We're going to be focusing in this course predominantly on RxJava because that works well with Android. But be aware if you are programming for non-Android environments, you're probably better off with Project Reactor because it tends to use newer, cooler features of Java streams of Java functional programming features than RxJava for reasons we'll talk about later in the course. So all of these frameworks I just mentioned, so things like the fork join framework, the streams framework, parallel streams framework, completable futures framework, the reactive streams framework, those can all allow you to do parallel processing without having to have any locking or much locking, and without having to have any or much threading explicitly in your code. In fact, all the things we're going to be doing in this course from a programming point of view will all be done without any synchronizers and without any explicit threads. And that is really cool. And the reason why that's really cool is it helps to alleviate many inherent and accidental complexities of parallel programming. So a lot of things that would otherwise make you go crazy and have all these low-level niggling details that would distract you from the actual requirements at hand are handled for you by these frameworks. And as we'll see, they're handled for you in a way that doesn't throw performance out the window. There's always this trade-off in computing platforms, computing languages between programmer productivity and computer productivity and computing productivity, infrastructure productivity. And the Java frameworks do a pretty good job of balancing those trade-offs. Under the hood, the parallel streams and completable futures framework use the fork join pool as the underlying computation mechanism. The various reactive streams frameworks can use that if they choose, but there's also other types of frameworks and concurrency models that they have under the hood to run things in parallel as well. So that's the end of the discussion of how parallel programs can be developed in Java. This is really the key summary of what we'll be covering in this course, because we're going to be covering, of course, the parallel streams, completable futures, and reactive streams implementations. So this is kind of a preview of cool things that are coming down the road.